now we can start the webinar. So welcome all. Thank you very much for joining today. We have a topic, scientific visualization using ParaView, data analysis, visualization techniques, and programming workflows. I would like to ask you to turn off the cameras and mute your mic if you're not speaking. And if you have any questions, write them in the chat. We have a live chat during the webinar. And also we have started a survey. So I would like to ask you also to complete it in the chat. You can find it. That helps us to fit the webinar content to the attendees, to their background a little bit better, understand your background a little bit better. So it's useful for both sides. And I would like to start with a brief introduction or explanation of what WiredWhite is about, or what we do and why we do it. So WiredWhite is an engineering platform. It's sort of an engineering network that we have created and built up. And we have basically on the right hand side a diagram explaining the concept, explaining the platform. So basically, we have two different type of platform users. We call it customers and partners. So what customer can do on our platform, he can get a private tutoring, he can get a mentoring. So you can imagine a customer is typically a bit less experienced engineer, or it can be a student, or it can be also an industrial project customer, so a person that needs support with their daily tasks or projects. So again, customer can get a private tutoring on our platform. He can take online courses, and he can also read technical articles, white papers, blog articles that our partners, our community members publish. And he can also attend these sort of online free webinars where we try to educate our community and share the knowledge. And once they get a little bit more experience, they can transit to become a partner. So what partner is a more experienced engineer that has a little bit of industrial experience, or much more industrial experience than the customer. So what he can do on the platform, he can provide, give private tutoring and be a mentor. So he can teach customers. He can also create and sell online courses on the platform, and he can also join industrial projects, consultancy projects with industrial customers or with companies, and help us to succeed in our R&D projects, in our industrial projects. So this is basically what partner gets using our platform. And we strongly believe that it helps also for the electrification worldwide, for the global electrification. This is basically the reason why we have launched this platform, this engineering platform. And I would like to go to the next slide and introduce our speaker today, Cesar Jimenez Navarro. Cesar is an aerodynamics engineer at Airbus Defense and Space in Getafe, Spain, where he contributes to the design and development of next generation military aircrafts. He holds a PhD in fluid mechanics from the Institut National Polytechnique de Toulouse. His doctoral research advanced the understanding of transonic buffet phenomenon and morphine wing concepts, and also the turbulence modeling. Alongside his research, he's also he has industry experience and industry work. Cesar also deeply engaged in teaching, obviously, and knowledge transfer, knowledge sharing. And he lectures also in thermodynamics and fluid mechanics at Universitat Carmenali in Andorra. And he has created widely used online courses on that, also on Python-based CAD automations and scientific visualization. And his teaching journey has also included roles at INPT in Toulouse and also Linköping University in Sweden, where he mentored also his students in CFD as well and aerodynamics. And with his experience spanning programming, CAD, and CFD on the other side, Cesar brings both technical depth and the passion for education to his professional endeavors. So I would like to welcome you, Cesar, to today's webinar. You can share your screen now. Start with the slides.
Perfect. Thank you so much for the kind introduction. I'm going to share my screen. Wait, the whole screen. Screen 2. Okay, guys, can you hear me and see me? Okay,
yes.
Can you see the screen?
Yeah.
That's perfect. Okay, so hello everyone. In today's talk, we're going to dig into the topic of scientific visualization alongside with what is ParaView and how to use it. And I prepared this talk in such a way that this will be the talk that I would like to have had when I was starting ParaView, you know, because when I started using ParaView was when I had to present an assignment, do a work, so everything was like super rushy. Sometimes I didn't have the time to really look into the documentation, and also like I didn't have any clear introduction into the topic. So I hope that after this talk, you might have like a better overview of what ParaView is, how the environment is structured, and maybe like you might give it a chance to use it when you are doing your own post-processing. So this talk I divide in four main points. So I'm going to give you introduction, like a theoretical introduction to what ParaView is, what scientific visualization is, and which is the data model, which is embedded into ParaView. Then we're gonna do some basic examples in the graphical user interface of ParaView. So I will leave the presentation. We will play a bit with ParaView, and I'm gonna show you how to use it. And then we're going to reproduce the work from section 2 by using a script. So you will see that everything that has been done in the graphical user interface can be also achieved by using scripts. And finally, we will finish with some conclusions and takeaways. So let's start with the fundamentals. So what is ParaView? So ParaView is an open source platform for scientific visualization and data analysis designed to process a wide range of different large complex data sets. So can be used for aerospace applications, but not only, can be also used in medical applications, weather forecasts, multi-phase simulations, building aerodynamics, and also sport aerodynamics. So it's not linked or it doesn't have like a unique area of specialty. It's a software that can be used widely. And if you have any kind of data set, probably in ParaView, you can load this data and render it in a nice way. So many people get a bit overwhelmed by the environment of ParaView and how it is structured. So I created a slide, and I hope that after this is clear. So in ParaView, you have these main executables. Okay. In this seminar, we're going to focus on the ParaView client, the graphical user interface. That maybe if you already played with ParaView, you already know it. And also, we will see a bit of PyPython. Okay. These executables, what they do is through a set of user interfaces, they communicate with the ParaView server. Okay, so it's like a server that when you start ParaView, a session starts, and this is the abstraction layer, right, which is used to communicate with the visualization toolkit, okay, which it's a collection of algorithms that permit us to load this data and represent it graphically. And this visualization toolkit, okay, it depends on open source libraries like OpenGL, MPI, which consists, which permits to run all this environment smoothly. And with this slide, you might be thinking, oh, but do I really need to know like in detail how everything works? Well, no worries. If you are a basic user and your objective is just to query some data and basic information, okay, you might be just using the ParaView client, which is the graphical user interface that we will see today. If you are performing like some advanced post-processing, you are not doing some automations, you are doing batch processing, or you want to build your own apps, you might be quite experienced or familiar with these other executables and also like the wrappings to communicate with the ParaView server. And then if you really want to dig into the topic, you might get familiar with the ParaView server, the visualization toolkit, and all the libraries below that are used to compile this environment. Personally, I will consider myself an advanced user, but I think that throughout the years, I would like to get more and more. I would like to dig deeper into the topic, and I might start like developing my own VTK applications, but I guess that will take me like some time. Okay, regarding the executables that I just briefly mentioned, we have these main 5. The first is ParaView, which is going to be the focus of the seminar. So this is the graphical user interface that basically allows us to do all kinds of operations. Okay. Then we have PyPython and PyBatch that allow us to automate tasks by using Python scripts. And the difference between these two is that PyBatch supports parallel processing in supercomputers, so in HPC resources. Then we have the PV server, which is the server which is executed for remote visualization. So we can connect from any of these 3 into the server in case we want to do remote post-processing. And then the difference between the PV server and the PV data server and PV render server is that these two do the same thing as the PV server, but the data processing and rendering is done in 2 different hardwares. Okay, this is like an overview, but in this seminar we'll focus on these 2. Before moving forward, I think that we should clarify what scientific visualization is. And we know that visualization is the process of transforming like data that can be stored in your computer in the form of byte, ASCII files, or whatever, and we transform it into a way that the humans can interpret. Okay, so we can display graphs, we can display contours, renders, tables, and so on. And this process is key because later on will have a huge impact on any design process, right? So correct visualization is key in order to take the right decisions later on. So that's why personally I spend a lot of time, trying to pick the right angles, the right legends, how the figures are shown, because that's gonna make such a difference when you will sit down, analyze the data. That's why I think it's like a very key part of the design process. ParaView uses under the hood the VTK, which is the visualization toolkit that I mentioned before. And it is basically the visualization engine that allows us to load the data from our hard drive and display it in the screen. Okay, so I will just explain what the VTK data model works, because this is key in order to understand how ParaView works. So first thing is we need to understand that in VTK, like the core data structure is the data object, okay, which can represent a scientific data set or something more abstract like graphs or trees. And this data object has 2 components. One is the mesh, okay, which defines the topology and the geometry, and other are the attributes, which is the data associated to each cell in the mesh. So the first, which is the mesh, it's like a group of cells. In this case, we have 2, which are defined by a set of points and the way they are connected. Okay, and this way of connecting is called as obviously as connectivity. In ParaView, you can define points or cells. Okay, you cannot define edges or faces. They are derived based on the connectivity of the mesh. And then on the other side, we have the attributes, which are the discrete values which are associated to the mesh. Okay, in ParaView, we can have arbitrary number of components. So we can have a scalar. So 1D variables like pressure or temperature. We can have vectors like in 2 or 3D components like velocity fields, or we can have tensors with more than three dimensions, like the distress tensors. Also, regarding the attributes, we have like 2 kinds of attributes. We can have point center attributes, or also known as point data within the software, where the data is stored on the vertices of the mesh. And if you want to know the value anywhere else, this value will be achieved by using a certain interpolation algorithm. And then on the other side, we can also have cell-centered attributes known as cell data in ParaView. And basically, this assumes that the value is constant throughout the whole cell. Okay, so there's like not a smooth transition like we could have in the point data. Also, this data can be loaded into ParaView in different ways. We can have a uniform rectilinear rates, where we have elements, or we have cells which are aligned with the main direction, so X, Y, and Z, and they have the same size. So this will be like rectilinear, so uniform rectilinear. We can have like non-uniform, where basically we have different sizings in the main directions. We can have curvilinear grids. We can also have polydata, where we have this can be, so this is data which is a polygonal, so you can have points, you can have edges, you can have triangles, pentagons, you can have any kind of polygonal data. And then also we have unstructured grids. Okay, so this is like a collection of cells which contain data, and this can be points, can be edges, and can be other complex shapes that you can achieve through points and edges, right? So we can have pixels, we can have voxels, we can have hexagonals, and so on. And maybe here you might be wondering, okay, but which is the link between polydata and unstructured grid? Well, this one can hold, it's like a data structure, so it actually holds attributes, whereas the second one, the first one, polydata, it's especially designed for visualization. Okay, so when you load data into ParaView, you might be loading an unstructured grid, but actually what is going to be rendered and displayed in the computer is going to be a polydata. Okay, so this process is achieved through the method extract surface, in which the unstructured grid has some faces and edges associated, and therefore you can convert it into polydata. And you can also do the opposite change by using the method clean to grid, and then you can convert a polydata into an unstructured grid. Right, so this is the bridge between both these types. One is for holding data, containing data, and the other is optimized for quick renderings and visualizations. We can also have AMR datasets, which is a collection of rectilinear uniform grids, okay, with different degrees of refinement. We can also have multi-block datasets, in which we can have multiple datasets together, okay, with different attributes. And then we can also have multi-piece datasets. The difference between these two is that both of them can have multiple domains, but the difference is that multi-piece is specially optimized for parallel visualization and computation, okay? When it's quite common that when you're running a heavy simulation, you need to use multiple CPUs, and you need to distribute your computational domain into multiple CPUs. So what you actually do is like you send chunks of the domain to each CPU. you will solve it, and then you will recover those chunks in order to visualize them. Okay, and here the key, so the requirement to have a multi-piece data set is that the mesh, so the mesh type and the attributes have to be exactly the same. Okay. In a multi-block data set, you can have maybe like a curvilinear grid. Here you have a rectilinear grid with different attributes of fields. Okay, that's totally fine in a multi-block dataset. But in a multi-piece dataset, the attributes and the grid type have to be exactly the same. And then obviously we can have tabulated data. Okay, so we have data with some headings, columns, and values associated to each one of these fields. Okay, in ParaView, because we're using the BTK algorithm, the BTK algorithms follow the data flow paradigm in which we feed data into our system or our session, and then we transform it using different algorithms until we are happy with the result, and then we can extract the useful information out of it. Okay, so here I've represented basic the visualization workflow. So in first place, we will have what is called sources, which are algorithm. Oh my gosh, today I'm a bit I'm mumbling a bit. The first is source, which are algorithms that feed data into our session. Okay, can be a file reader or geometry generators like a sphere or box. Okay, so it can be algorithm that will read our depth of file or inside file or inside the file or our simulation data, and then it will load it. Or we can also have predefined geometry generators like sphere boxes that will create a data set that we can use later on for multiple purposes. So once we have our data set, we can use it as an input of different filters, which are other algorithms that transform the data in different ways. And finally, we have the sinks, which are algorithms. My God, how am I today? Algorithms without any kind of output, because what they do is they convert the data into graphics, like the ones we can see in our screen, or also files that are stored in our disk. Okay, so I hope that I was not too boring with the theoretical aspects of ParaView, and now we're going to go towards something more fun, and then we're going to start playing with ParaView a little bit. Okay. So we're going to see a few examples. Okay, the first is going to be pretty basic. We're going to see how the graphical user interface looks like. We're going to load a sphere, perform some operations, and then we will prove some data. Okay, so I will just move this aside. Okay, so this is how the graphical user interface looks like. For some people, it might be overwhelming. I can agree to some extent. At the beginning, like when you don't really know how to look at things, can be a bit confusing. But the algorithms that I just mentioned before are basically, you can access to them here. So you have, first of all, sources. You have also the filters, and then you have the sinks. Okay, in each of them, you can access to them in alphabetical order or to different kinds. Okay, so as in here, here we have all the filters which are available in ParaView, which is, you can see, quite overwhelming. But personally, my favorite way to access to these filters is if you press Control Space, you will have a menu. Okay, and then here you can type which filter you want to call. Okay, so in my case, I want a sphere. Okay, so this will create a sphere filter in my case, in my pipeline. Okay, here we can play with the theta resolution, phi resolution. Okay, and then this. So this is an algorithm that has a pre-programmed pre-programmed data set in order to generate spheres. Okay, So here we have our sphere in the ParaView section, and then we can represent this data set in different ways. So we can maybe display only the points. We can display the surface, which is the option by default. We can have we can display also the edges. Okay, and also if you want to provide data, in this case we don't have data because we have loaded a geometrical data set, so we won't have data, but we can access to the coordinates of it. So here on the top menu, we have this red button, okay, that allows us to, if we hover over certain points, we can access to these properties. So in this case, we have the coordinates of each point and then the normals of the face. Okay, we can also access to the whole cell. In this case, this filter only creates point data, so that's why we are not seeing any cell data. And then we can also pick them like this. Then we can pick multiple values, and then here we can visualize some of their values. And then also, if you want to keep them for future analysis or to use it as a seed for other filters, we can press the button extract, right? And then we will have these points extracted. I'm not sure if you can see them. We just increase the point size with. Okay. We put it as spheres. Point size be 20. Okay. So we can use these points later on for other things. Okay. So here you have like plenty of options. And if you want to remove the selection, you can press here selection, and that's it. Okay. So we have this data set. And then to it, we can apply different filters. So we're going to do something super simple, which is to apply a basic transformation. Okay, so this is the transform filter, which allows us to maybe like rotate it, scale it in one direction. We can move it in the 3D space. Okay, so we can either do this manually, or we can here set the values manually. Sorry, set the values one by one. Then once we are happy with the final result, we can press OK, and then we can see that the sphere went. So this data set went from this initial shape to this final shape. Okay, so we have done scaling, rotation, and translation transformation. Okay, perfect. Okay, so pretty basic sample.
We got a quick question, Cesar, from the chat. If you could explain again how to get that sphere displayed.
Yeah, that sphere. Yes. So let's start this again. Okay, so what you can do is if you press Control Space, okay, you have access to all these tools, and then if you type sphere, you can see the algorithm that is used to generate this data set. So you press OK. Okay, and then here you can set the resolution for the sphere, and then you press apply. You can either press apply every time, or I think here there is a button which is the auto apply. I think there's a button. Yeah, apply changes to parameters automatically. So here, every time you do a change, it will apply automatically. Personally, I don't like it, but it's really up to you. Okay, I think it's clear, right?
Right.
That's great. Okay, so let's move to the next example. In this case, we're going to do something a bit more complex. We're going to load some data. We're going to display the pressure coefficient, also the skin friction in a secondary field, and then we're going to in a secondary representation, and then we will save this figure in our computer. Let's see. Just like do this. 1 sec. Okay. Also, another tip: if you press Ctrl R, you can reset the current session, so you don't actually have to close the program. Okay. This is like very handy. Okay, let's load the data set. This is aircraft surface data. Okay, the reader. Okay, so this is our pipeline. Okay, and then I think I lost. I lost the information. Wait a sec, because I closed a toolbar by accident. Properties. Thank you. Okay, so this is my dataset. So it's like a simulation over an aircraft. Once we load data, here we can choose which data rates we want to load in your session. In case that you have like plenty of variables and you want to have like a more clear, a cleaner design space or like working environment, you can pick which values you want to load. In this case, we're going to just work with 2 variables. So let's go ahead with this. And then here what you can see is that this aircraft has really funny colors. And this is because this simulation was performed in a supercomputer. So we have divided this computational domain into multiple elements and then into multiple blocks. And then each block is sent to different CPU and in order to perform the simulation. So what we have here is that we can see that we have a multi-block dataset. But in this case, we won't need to group them, but later we'll see why it is necessary. So we will do that in the next example. Okay, so here on the top bar, we can select which is the color in which this surface is represented. By default, is the BTK block colors, but we can represent it by the pressure coefficient. We can represent the skin friction. So let's select the pressure coefficient. And here we have like multiple options. We can set a custom range. So let's do it from -1 to 1, for instance. Okay, so we can clip these values to a desired range. We can also only rescale to the visible data range. So basically, all these cells or points that are being rendered, you will take the maximum and the minimum. Okay, so you press this, and then the color bar will be adjusted to the ranges found in the rendering style. So this is we have here given limits, but if we turn the view and then we press again, we will have different ones. Okay, so this depends on which data is being displayed. Also, we can reset it to the minimum max global data. But personally, I like always to use a range in which I have a better understanding of what it's actually showing. Okay. So here, just like to see what is going on, we have this aircraft is flying at Mach, if I am not mistaken, Mach 0.2, so transonic regime. We have a clear shock over the wing. Okay, so this is how it looks. This is where the shock terminates. So here we have like an abrupt pressure change. Yeah, this is like the main stability, the main flow feature that we can observe here. Okay, so here on the top bar, we can have access to the color editor. Okay, so, oh my gosh, why is it not? So maybe it's, yeah, I think this screen is like too small for this seminar. Okay. Okay, so with this, we access to the color map editor. At the moment, we are working with the pressure coefficient. And then if we press here on the heart, so it's called a choose percent, we can select which color map we want to apply in our representation. Okay, so personally, I like this one, which is the version, because we want to highlight low values and high values. Okay, so we can have this one. And then also this is the color map. We can either put it manually in a different position of the screen, or we can have a more accurate control, which is here. Okay, you will have this menu. And here we can select, remove the option auto orient. We can make it show horizontal. We can control where it is shown. So let's do upper upper left corner. Okay, let's see how it looks like. So at the moment it moved here. Then if maybe like if some of you is doing a research, you know that well, some of you who is doing research, or some of you who's using LaTeX, you can use it in within a ParaView. So imagine here we can use the mathematical notation. Then we can maybe like apply different text sizes. So let's do here. Here we can also like modify the thickness of the bar. So like this, like with this, all these little changes, you start giving the color bar like the shape and the appearance and the location that you want to have. We can remove the automatic label format. Personally, I like to just maybe like for this case with 1 decimal is enough in float format. Oops. Okay. We apply the same here. Okay. So now we have this color scale. Okay, which already looks quite nice. And then we can select this option. This also here we have access to the views, to the multiple view presets. And well, this already will look quite nice for a CP investigation. But let's say that we want to show more contours or more information. What we could do is like we did in the previous example, we can use the transform filter in order to show the aircraft symmetry and show more data or different data. So we will use again the transform filter. Okay, we can scale it. In this case, we're going to do it manually. We will do it in we will scale it negatively in the Y direction. Okay, let's press apply, and then we can see. Let's show both of them, and now we can see like the full aircraft. At the moment, both are shown in both CPs display, but we can display different contours in different filters. So in this case, we can show the skin friction coefficient. Okay, let's go back again to the color map editor. Oops. Oh, by the way, this icon is to hide or reveal the color bar. And then we can go here and similar process before, can be horizontal. Then this time it can be, we can do it lower left. Okay, then let's do it same kind of style. Okay, this will be 25. Okay, then this will be floats. Okay, let's apply. Okay, and then it will look like this. But also, like personally, I sometimes don't like to have the orientation access here. So maybe if you want to remove it, you can go into the properties options, properties window, and maybe I forgot to talk about this. In ParaView, you can have everything. You can see everything in the properties window. But it is important that if you want to have full access to everything, you should like toggle the advanced properties, because like that you can have access to all the options. Okay, so in this case, I want to have access to the orientation access visibility. So like this, I will remove it. Okay, so let's go back to the CFX. I think in this case, because we want to show in which areas we are going to have recirculation and in which ones we don't. So let's go to the color map again. In this case, we will choose a different preset. In this case, because we want to see again where we can see like complete different behaviors, we want to use a preset that really highlights these differences. And personally, I find quite useful the cold and hot preset. Okay, let's do this. And then we want to have it centered in 0. So let's do minus 0.001 maybe. Minus to 0.001. Maybe it's way too much. Okay, yeah, I think it looks good. Okay, so what this contour is highlighting in yellow, we have areas where the skin friction goes in the actual axis, so that means that the flow is attached. Whereas in the cases we have like blue zones, we have zones where the flow goes, so the skin friction is in the opposite direction. So therefore, we can see the presence of some recirculation bubbles. Okay, so it's like an example of how to get quick insights by using this kind of very abrupt and sharp color maps. Okay, so once we are happy with our color maps and configuration of layouts, we can always go to here, save a screenshot, and then we can save the image in the format that we want, and also we can choose the resolution of it. Okay. And like that, you can generate images for your presentation like this one. Okay, hope that this example is clear. I'm not sure if I went too quickly. If you have any question, please, you can stop me at any moment. In case that you are trying to follow or do it in parallel, please let me know if I want to, if I have to clarify something. Okay, now we're going to go towards a more complex, relatively more complex example. Oops, I think someone asked something. Okay, maybe like all good.
Oh, it was just thumbs up.
Okay.
Now we have a question.
Yes, how to export simulation data. Oh, I missed it. How to export simulation data directly from Fluent to ParaView. Okay, in this case, I use a lot Nsight. With Fluent, you can generate Nsight files, and ParaView can open these Nsight files. So I think the format is called Nsight Gold. Yeah. So to try it, and yeah, it should work like 99%. Okay. In the color bar, if we don't want the left end of the color bar that is too dark, there is a way. Okay, we don't want the dark left. What is the dark left? I didn't get that. Do you mean like this dark color?
Yes.
If you can. Yeah. Tell me.
Yeah, in the color bar, sometimes the lower end or the left end is too dark, and there is a way to start it not from that dark color, but from somewhere in between. So
yeah, I mean, I guess that you can, if you want to.
Yeah, yes.
Also, like play with custom. I just don't. I'm a bit scared of like, because I'm not super familiar with this, but you can maybe like play by hand with this. So you can, you can definitely modify this by hand. And adjust it until you're happy with the results like that. If you set this, you play also with transparency. Yeah.
Once you move that, I couldn't apply it. So once you move that, does it apply automatically, or?
You mean these points?
Yeah. Okay.
Oh yeah, you need to use enable opacity mapping.
I see. Okay.
Yeah, so you can press with this, and because it moved, you can see that it is transparent. So you will need to readjust again this. So maybe like from minus 0.9 to 0.9. Yeah, well, you will have to play with this a bit. Yeah. Okay. Yeah, this is a way to move, to play with the color maps. Yeah.
So thank you. Yeah.
You're welcome. Okay. So now we move to the next example. Okay. Let's load it's the same dataset, so I shouldn't have reset the session. Okay, we are here again. Sorry. Okay. In this case, we're going to load the pressure coefficient. Okay, and imagine we are asked to study the pressure over certain locations of the wing. So we need to extract the profile of the wing and then display some properties over it. Okay, so let's do that. In this case, we will need to slice the wing. But maybe what you might notice is that if we slice the wing in this direction, we might also slice the horizontal stabilizer, and we don't really want that. So first of all, we need to apply a clip. Okay, so it's a clip, and this is a filter that allows us to extract some to extract a domain based on a physical constraints or a box. So in this case, it's apply. Press apply. So we have clipped our plane, and then the next step is to slice this way. And for that, we'll use the slice filter. Okay, here we can put it normal to the y-axis, so in the, normal to the y-axis, and then we can also place. Wait, maybe let's do it closer so we can have like a thicker profile. Yeah, let's do it closer to the fuselage. Okay, but here we update it. Okay, so the moment. So we have this, we have extracted this profile with this slice. Okay, the next step will be to visualize this data on a graph, and for that we have the filter plot data. And if we press apply, okay, because it's a graph filter, what will happen is that you will have a new view. In this case, it's a line chart view, and then we can represent information. So we can present the graphs. So we can select which fields we display in the x-axis and then in the y-axis. So normally we can display the points in x, and then we can also display the CP in the y-axis. But what happens? Like, this is quite messy, right? And you can see that something is fishy, something is not going really well in this position, and it is because we have skipped one step. And remember that we have a multi-block data set. First of all, we need to bring it together in order to be able to slice and perform all these operations correctly. So let's go back a couple of filters. Okay, so in this step, we need to do the merge filters, merge blocks. And this allows us to move from, here we go to here. One sec. Here we go here. We move from a multi-block data set, and then after applying the merge blocks, we move towards an instructor grid. Okay, and this is what we want. Then again, I will do it quickly. I will press the clip. I will use the clip filter. Okay, let's extract the wing. Perfect. Then we will slice it. Okay, normal Y. Perfect. And then we will do once again the plot data. Perfect. And then once again, so we have this data. And then we display it. So we display CP or X. And then we see again, okay, but this is still, it looks like quite valid, right? And the problem here is that we're representing these points in a random order. Okay, so ParaView for now doesn't understand which is like the logic in connecting all these points. But thankfully, we have another filter, which is called plot on sorted lines. Plot was. So if you write sorted lines, is the only one which is available. Okay, so we click in plot on sorted lines, and then what this filter does is that by connectivity, by looking for the closest cell, it is able to reproduce the full envelope of it. So now if we represent on the x-axis the axial coordinate, sorry, we can see better the pressure coefficient over this slice. Okay. And also maybe it's better for us to invert the y-axis, and for that we can have access here to, let me see. Oh no, wait, sorry, I have to be here. Also very important in ParaView. It will always, so in properties, you will always have access to the properties that of the selected filter or the active window. Okay, so in this case, we can select this this window is highlighted, we are working in on this view. But if we move to the other, we're working on the other view. Okay, so if we access here, we press advanced properties, and then here we can have access to all these options to modify the configuration of this axis. So, for instance, on the left axis, we can select the minimum and maximum range, and also we can invert it by setting as the minimum a positive value and the maximum a negative value. Okay, so that we can invert the orientation of this axis. It's like a more common way to represent the pressure coefficient or the pressure distribution over a profile. Okay, great. And I think we can also, I think we're a bit short on time. We have only 10 minutes, so let's cover the last example. Yeah, this is a bit more complex. Okay, so in this case, we're going to compute the lift over a wing, and for that we need to understand how these forces, where these forces come from. So obviously these are pressure forces due to the pressure difference between both sides of the wing. The lift is the force which is normal or perpendicular to the flow direction, and then the drag is the force which is parallel to the flow direction. And these forces can be obtained by doing the following projections, okay, by using the force in the X and Z axis. Okay, and these forces are computed by the following, like using the following reasoning. We know that the force, so the force acting over an element on a wing is proportional to the pressure difference between the local pressure and the free stream pressure. Okay, so this, I'm gonna call this term relative pressure. Then we know that the pressure is the force over a surface. Okay, so the way to compute the force over this surface is to multiply the pressure acting on it times the area of the element times and then you multiply it by the normal vector in order to give the direction, which is always normal to the face because the pressure acts normal to the surface. And then once you have all these little forces in every single cell of your computational domain, you need to sum all these contributions. So you need to perform a numerical integral. Okay. We are not solving this integral numerically because we have done a simulation. We have discretized our flow field into computational cells. So we're doing the summation of all these cells. Okay. And this will be done by using the integrated variables filter. And why am I leaving this expression here too? Because as we will see later on, this is like a very interesting source, a very common source of confusion in ParaView users, that in the integrate variables, there is an option which says, do you want to divide it over the area? And in this case, we don't want to, because we want to have this quantity. If we divide it by the area, what we are doing is we are computing the area weighted average. Okay, so we are computing, we have our quantity, we multiply by the local area, and then we divide it later on by the area of the surface. Okay, so this is not what we want. We want the first event, so the first expression, the numerical integral. Okay, so let's go. Let's do it quickly. Okay, so let's load the last dataset. It will be transforming in section. Okay, take the reader. I'm going to use in this dataset only the pressure variable. Okay, so this is a wing section. So it's like a transonic airfoil. And then, like we did in the previous example, first of all, we need to bring all the blocks together. So we'll do the merge blocks filter. Then we will extract the surface of this data, extract surface. And then we're going to use a new filter, which is called surface normals. Okay, what this filter does, it computes the normal direction of the vector of this face, surface normals. Yeah. Okay. And then we have the pressure that we have loaded, and then we have also normals. Okay, which are, we can see them by using the glyph vector, the glyph filter. We can orientation array. We want normals. Let's see how it looks like. Voila. Okay, if we press it, all the points. Okay, so what this filter does, it creates by every single cell an arrow, so it computes like the normal vector. Okay, so all these are arrows that are pointing outwards of the surface, which is going to be essential because later on when we compute the local force, we have to give an orientation which is going to be normal to the surface. So it's going to follow this vector direction. Okay, so now let's start with the calculators. At the moment, we have only this variable, which is the pressure, but we need to extract other variables based on this. So for this, we will use the filter calculator, which allows us to perform datasets modifications by modifying its data. So I'm going to create a variable pressure relative, okay, whose formula I have it here, so I don't spend too much time typing on it. Okay, which is going to be the local pressure minus the reference pressure. Okay, so like this, we have the pressure difference. Then what we're going to compute now is the pressure forces for which we're going to compute. We use another calculator. Let's call it the pressure forces. Okay, which in this case is going to be the relative pressure acting on each element times the normal. And in this stage, I am not multiplying the local area because later on in the integrated surface filter, it is automatically multiplied by the local scalar. So by the local area, sorry. So later on, the integrated variable filter that we're going to see immediately after this, what it does, it takes our variables in the data set, and then it performs a summation by multiplying by the local area. So if at this stage in the calculator, we add the contribution of the local area, we're going to have it twice. So therefore, our calculation is going to be wrong. That's why for some people, the integration values tend to be quite low because they multiply the cell, so the local area here, and then it's multiplied again. Okay, so we have here. And now, if we show it the vectors again, we say orientation array pressure forces, scale array pressure forces. Okay, we set it here. Oh my gosh. Okay, so it should be way lower. And -6. Please tell me this works. No, maybe like, well, actually, that's not too bad. Let's do one less. Okay, and now in every single cell, all points. Okay, so what we are visualizing here is actually the forces acting on the wing surface. So let's also show the solution. Yeah. So what we have here is like if the arrow is pointing outwards, what we're having is we have a pulling force. So that's why the top part of the airfoil is called suction side. Whereas if we have an inwards arrow, that means that the force is going against the surface. So we have here some pushing forces. Okay, and the resulting force of all these arrows will be given by the integrated variable filter. Okay, so like that, we close this. We go to course called integrate variable filter, and then what we have done. This is the cell that I mentioned before. So we don't want to divide it by the cell volume. We press apply. Okay. And then what we see here in pressure forces. So here we have the forces in different directions in newtons. So we have in the x direction we have a force of -33 newtons. In the lateral direction it's almost negligible. So it's very, very close to 0. And then in the set direction, which is the main component, we have the lift contribution, which is nearly 600 newtons. Okay, so this is like a quick and easy way to obtain the pressure forces over an aerodynamic surface. Great. And I am afraid that I don't have the time to go over the scripts. I thought this section will be way quicker. That's my bad. Okay, so the goal was to reproduce exactly the same. So if any one of you is interested, please you can send me a message so I can send you these the scripts. Okay, so I will jump directly to conclusions. Okay, so we have, do you have a question or?
I think someone wanted to speak.
Yes.
David, please go ahead.
Oh. Mm-hmm.
Sure, I wrote the questions in chat, but
yes.
You can ask them again. Is it possible for us to get access to the aircraft data you have for?
Yes. From my side, there's no problem. I'm not sure, Dimitri, can I send it to you so you can upload it online, or how do we do it?
Yeah, sure.
Yeah, for me, there's no problem. You can have this data set for practicing.
We will send over all the presentation slides and also include this aircraft data, so you'll get it.
That's great. Yeah, since it's surface data, it's very light, so there should be like no problem in transferring the data.
And the other question I had, it was, you just showed us the example that it comes doing the calculation already in newtons.
Yes.
The question would be, does it depend on the data we're using that the calculation ends in newtons, or will it always be transformed to newtons?
Yeah, well, in my case, because I am working in pascals, okay, the thing is that I have omitted the details of this calculation, but I am working in pascals and a square meter, so at the end, you end up with newtons if you perform these transformations and equations.
Okay, thank you.
Yeah, you're welcome.
Yeah, thanks, David. Hamza is asking whether we are getting the recording. Yes, you will get that after the webinar.
That's perfect.
Anyone else? Guys, it's the best time to ask Cesar a question. The live webinar, so we can approach it right away.
Okay. Yeah, because I don't think I will have the time to do a lot more. I'm already over the time.
I think previously I have received more like a general question, or your based on your experience or your expectations. I posted it in the chat. So what is your current, let's say, vision on trends in scientific visualization, especially regarding AI? So pretty interesting question, I guess.
Yes. So, I mean, regarding AI, I haven't yet found like an AI agent or AI service that does like all the visualization, because at the moment it's really up to one person or up to every single of us how the data should be arranged, organized, so for us to understand it. And I think that's quite personal. So I think that maybe like in the future, like there will be like more and more agents capable to understand which are the requirements and how data should be displayed for like a general public to understand it. But at the moment, I think that's going like relatively slow. Okay, we have some examples, but I think that it needs it needs some momentum.
Right.
Yeah.
And we have one from George or Jorge. Which CFD software do you use in your work?
Yeah. So well.
Transfer.
Yeah. So I cannot personally like talk about work per se, but I can say like what in the past. So I used a lot in the past Fluent. I used OpenFOAM. I used the Sim Center. And during my PhD, I used an in-house code, which is called Navier-Stokes multi-block. And regarding the data formats that I've used mostly have been TechPlot, quite a lot, MSite, and very rarely CGNS. CGNS, which stands for CFD Generical Numerical something. It's like like a standardized format, which is quite heavy. Yeah. So I think those are the main ones that I've used.
Right. Yeah, thanks a lot. So I think we have a conclusion slide, right? Left.
Yes, exactly. Okay, I have it here. Well, I guess you guys already have read it. So what have we seen? So we know already that what ParaView is. So it's like a powerful open source platform for scientific visualization, which even though we have been targeting CFD a lot in this webinar, can be used not only for CFD, but also like structural analysis, or I think it has been also some applications in chemistry and obviously in medical visualization. We have covered the essentials, so we have learned how to load the data into ParaView and how to use some basic filters in order to obtain meaningful information. This is the part that I couldn't talk about today because I ran out of time. I really wasn't expecting that it would take me like so long to do these 3 basic examples. And then as a takeaway and main and final conclusions, the good thing is that ParaView is that it's free, it's completely free, it's highly customizable. If you learn it once, later on you can, it's very portable, so you can use it later on anywhere. It's highly customizable, so you can really build your own scripts. You can adapt it to any workflow you have. But here, the problem of ParaView is that it is, it's not very beginner friendly. Okay, so you need to really understand the fundamentals in order to be able to use all the filters, understand what is going on, and if you have a problem, how to resolve it. Which is what most of the commercial platforms do for you, because mostly, I think like the most famous are TechPlot or Insight. They are like way more robust than ParaView in terms of functioning. But in my personal opinion, I would always prefer ParaView because you can use it everywhere for many applications. You can build your own things. And it is obviously up to you guys what you want to do. If you want to do something quick and standardized, you can go to commercial platforms. If you feel that you want to learn more and dig more into the scientific visualization, I would recommend you highly to try ParaView and play with it a bit. Okay, so this is everything from my side.
Thank you very much.
Yeah.
I will just quickly share my screen.
Yep.
Just to wrap
I will
it
stop
up.
sharing.
So, yeah. So I would like just to give you some information regarding like how you can go also a bit deeper into the topic or another CFD maybe topic or CAD. Which is covered on our platform, so you can explore our online courses. So it's another option how to get a bit more skillful and go deeper into that topic. And you can also, of course, always drop a message to Cesar and ask him to support your, let's say, concrete question, and you can also try to get your question answered by scheduling a private tutoring call with one of our experts on the platform. And for all of these options, we are providing you the discount code WiredWhite 10, which gives you a 10% discount for any of the activity that you would like to proceed with on the platform. And I would like to thank you all for your time today, for attending the webinar. I would like to thank you, Cesar, for giving us this speech, for the material that you have presented. It was very interesting. Also, this software tool, the ParaView tool, has plenty of options. I think you will take maybe for the scripting part, we can have a extra session or a next webinar also.
Yeah, okay, deal. Yes, definitely.
Plenty of options there to explore, a lot of filters, and yeah, it's very interesting. And would you like to spend a couple of final words from your side, Cesar?
Well, from my side, like, no, I think it has been like a very interesting session. Like, I'm so happy to have the chance to interact with unexperienced people on the software. I hope that this have triggered some interest on the tool. Please, like, if you have any questions about it or you need like some advice, please you can reach me out through email, LinkedIn, or any way you prefer, and we can chat about it.
Yeah, absolutely. Okay, guys, then thank you for tuning in. Thank you very much, and we will see you in the next one. Tune in into the next webinar that we have on the platform. Yeah, thanks a lot, and have a great evening.
Okay,
thanks, Cesar.
see you guys. Ciao, ciao.
Ciao,
Bye.
ciao.